invitation. So I'm going to talk about my personal journey on domain adaptation and simulators, but I want to start with a slide that I think everybody in this room have seen already. So we entered into our deep learning era thanks to 3 factors, I would say. So we had large-scale, fully annotated datasets, we had powerful hardware, and we had models, and we also invented new models. Think about generative adversarial networks. So really a lot of things has happened in the last decade. But for the purpose of this event today, we are focusing on data. And the point that I want to make is that, okay, now we've been talking about self-supervision, but yeah, before, for many years, we've been using to train our deep architecture, and even now, large-scale, fully annotated datasets. I'm doing computer vision, and this is clearly a limiting factor when we have to address problems like, for instance, semantic segmentation or object detection, because you really need precise annotation and high granularity. So the reason why I got passionate about this domain adaptation is because domain adaptation is a research field that tries to address this problem of lacking of annotated data. So what is domain adaptation? Many of you may know this already, but the purpose of domain adaptation is to learn discriminative models, let's say classifier or regressor, in a domain of interest, let's say a target domain. For instance, here, imagine that we want to build a pedestrian detector, but we don't have labels on this data. So what we can do is to leverage some information for another dataset that we call the source dataset, and we want to transfer knowledge from the source to the target domain. But which is the issue? The issue is that always, or very often, we have a shift among the 2 distribution of the source and the target domain. So we really need methods to address this domain shift. So this timeline can reveal my age, so it's not very nice. But I got passionate about this topic in 2009 when I found this survey. It's called a Survey of Transfer Learning, and domain adaptation there was presented as a sub-area of transfer learning literature. Even at the time, we were only playing with shallow models, but even with shallow models, we had technique to address this distribution shift. And there were also interest in the community for collecting data to prove the generalization capabilities of model. But the real revolution happened later on when deep learning came to the stage, and so tons, I would say thousands of architecture were proposed for addressing the domain shift, and so we had access to many deep domain adaptation architectures. So as I told you, I got passionate of this topic, and then I imposed to all my PhD students to work on this. Not all, some of them. Some they were willing to work on them, okay? And so what we contribute with respect to the scientific community, we propose, for instance, one possible strategy to address the domain shift that was like embedding inside the neural network some proper layers that align the source and target data distribution, similarly to what you see in the picture here. And we were kind of successful with a very simple approach that can be implemented very easily, but still competitive with the state of the art. We also tried another strategies that's a bit more important for what I want to show you today. That is a strategy of having generative models that translate data from the source domain to the target domain. Why it's a good idea to have a GAN that translates source images into target-like images? Because then the target-like images would have annotation. And this is what is happening. Of course, this is a demo of a technology that we have developed many years ago. But I mean, this is just to make a point that one strategy for domain adaptation is this translation from the source domain to the target domain. What happened in the last 5 years? It happened that we have reached in the computer vision community a very high level of maturity in addressing this domain adaptation problem. And in particular, we have technologies, we have models that address this domain shift for images in a very accurate way. This has brought us to address more challenging problems. For instance, this is the case where we have videos. And so nowadays, even with foundation models, domain shift exists. So if you run clip, it will be very good, but not extremely good. So you can still bring some domain adaptation on the top of clip. But the thing that I wanted to show you here is that domain adaptation in video is much, much more difficult because, for instance, for a human, it's very easy to see that the two videos depict the same action, but for a system, it's not, right? There is a significant domain shift among YouTube videos and video collected in a gym from a drone. But despite this, deep learning can do a magic game because we have performance that are around 80%. So the first point that I want to make here is that we are kind of ready to play with videos. The second point that I want to make is about some people in the community that have been trying to play this game of translating images from the source domain to the target domain. And they also saw, especially for people interested in autonomous driving application, an opportunity from the use of 3D simulators to generate synthetic data. Why you should use synthetic data from 3D simulators? Because you can gather annotation that are of very high quality, and you can gather annotation for several different tasks, for instance, segmentation or depth estimation with the same dataset. Couple of examples very popular in the computer vision community, the Cynthia dataset, and also the use of the Carla simulator. On the top of this data, synthetic data generated with 3D simulators, what you can do is to use generative models. This is an example of a method that is called Cycada. It's a rather old method, but the idea here was to translate data from the simulator to the real domain with a GAN, and then use this for the purpose of semantic segmentation. Cycada is rather low in the curve of the performance because over the year we have seen we have constantly improved the performance of this method. And here comes, let's say, the most interesting part of my talk, I think. So at a certain point, we look at all this in the community and we try to ask ourselves a more challenging question, and that is, do we really need this combination of 3D simulators and then, let's say, generative AI to perform a translation between the synthetic to the real domain? Can't we do something else? And the answer that we found so far, this is an open problem for me, okay? But the answer that we found so far is that for specific application, you can build neural simulator. So you can build neural network that somehow allows you to generate contents that can be controllable. And in particular, we study a problem that we call neural video game simulation. And if you want to summarize this in one sentence is, can we learn a video game? I would say the answer is almost yes here. So we started with a paper at CVPR 2021 that we called playable video generation. So you're given a huge collection of unlabeled videos, and you built a neural network. I feel guilty because I am the only one with deep architecture on slides. I will be very, very concise in explaining them. Anyway, so you built a neural network that is made of two key elements: a dynamic model that allows to somehow understand what is happening in the video in terms of action, and a generative model that allows to translate this information about action into rendered frame. The outcome of our playable video generation is a video that is synthetically generated, and it is obtained when the user make some command. For instance, move the player to the right, move the player to the front, move the player to the left. This is the idea, and this is how we achieved. So it's a zoom in of our neural network that is fully trained in a self-supervised manner. It's a network that learns to encode frames into a state representation and then learn to decode the frames and reconstruct them. But the magic happens in the dynamics network and in the action network because we are learning in an unsupervised fashion the actions that are happening in the video. And this is what we learn. So there is no supervision on action, and what we learn, each column corresponds to a different action, and as you may see, action 1, for instance, corresponds to people moving on the left. And this is the final results. So this is a purely data-driven framework, so we can feed our model with whatever the data we found, and so you can play a tennis match, you can move a robotic arm, and you can also, feed this with data from a regular video game. Of course, this was exciting, but there are several problems. First, it does not support multiple players. Second, it doesn't handle the camera movement. Third, it's relatively low resolution. The frames are rendered at very low resolution. So we wanted to improve it, and we did a year later. And we created another model that is called playable environment that allows to perform controllable video generation in 3D. So here we can control the movement of the camera, we can control the style of the field, and we can control the movement of the players. And network, of course, it's getting more complex. In particular, the synthesis module, it's based on neural radiance field that many of you may know this. And in this part happened the magic because you are really able to render a scene under different point of view. And this is the results. So we also created another data set with Minecraft. So we were able to exactly measure quantitatively if the algorithm was doing anything good. So the commands are the commands that are corresponding to the numbers, and the numbers correspond to different movement. And there are 2 players, so we can play with 2 people. We can change the camera position and render the scene, and you see this. And we can also change the style. So given the content on the row, we can apply the style that is indicated in the column for both data sets. Of course, we are never satisfied. And so we had the 3rd version of the model. And the 3rd version of the model is something that at this point, to me, it's really exciting. So we saw that there were limitations in our previous work. So for instance, we had no possibility of having a very fine control of the player and also of the balls. We had no intelligence in the agents. We have no game AI. We had no interaction among objects, and we also had very low visual quality. So we got another framework that is even more complex. Unfortunately, this is the negative side. So at the core of this framework, there is this animation model that allows to do something very interesting. So you can condition the generation with any type of signal, and the most interesting type of signal is actually text. So you can input some text, and you can create a video that is coherent with such text. You can input information about movement of the different object, and you can also embed information about the pose of the people. This is done because this animation model is a diffusion model that maps this control signal into some environmental state. But I wouldn't say much more for this. And these are the results. So we are able to move the arms and the legs of the player. We are able to move the camera. We are able to change the style. But more interestingly, we are able to feed some text, and then the video is generated according to the text. I've never seen so many tennis match in my life. I actually don't like much tennis, but we have to like it, you know. This enables this. So we can really play with the system. So for instance, on the right, you see two people that are that are given as input to two different strings, and they can play one against each other. We can also enable what we call the director mode, where we are basically defining the trajectory of the ball, for instance, or we are even saying something more subtle, like player 2 need to lose the ball, need to lose, for instance. Yeah, this I'm going to skip because I've said, but there is also some magic, not only on the animation model, but also on the synthesis module, because we removed some upsampling technique, and we add now videos that we judge of quite high quality. So I'm done, but I want to say something. So we gain experience among these neural video game simulators, and we believe now that we are ready to go outside video games. For instance, we would like to move towards, for instance, the simulation of complex systems. And I want to close maybe with this one. So I do believe that perhaps to overcome this data scarcity, now we are very, very close, especially for videos. So in my research group, by the way, this is a collaboration with Snap in California. So we've been playing on the blue line, right? We've been having features to enhance the controllability of video generation. And there have been people in the community playing on the red line, so improving the quality of video generation. And now we're going to go on the top right. How, when, we don't know. We're getting close. OK. This is outcoming at CVPR 2024.